I'll sketch how integrative design can optimize whole systems for multiple benefits to achieve radical energy efficiency in all sectors. Professor Joel Swisher and I teach this proven practice twice a year at Stanford University, 14 times so far. It applies orthodox engineering principles, but it asks different questions in a different order. It's the most overlooked part of the four-part energy revolution that is rapidly shifting the world from inefficient to efficient use, fossil fuels to renewables, fuels to electricity, and centralized to distributed resources. This needs no magic or miracles or new technologies. It needs just beginner's mind, whole system thinking, rigorously simple design, and meticulous attention to detail. Then getting it implemented needs competition, keen business skills, diplomacy, and relentless patience. I'll address mainly how to use energy far more efficiently than most experts expect. But we hear far more about renewable electricity. Its global generation in green has zoomed past nuclear in magenta, gas in blue, and now coal in white. In the first 6 months of last year, the world added more raw solar capacity than it had operating nuclear capacity built over decades. Throughout May last year, China added 3 gigawatts of solar power per day, meeting its 2030 solar and wind target 6 years early. India was 5 years early. Nothing in energy has ever changed this fast. New rules. Renewables keep getting cheaper as we buy more, because mass producing more equipment drives rapid learning. In contrast, mining fossil fuels causes depletion and raises political risks, so costs rise. Also, renewables deliver energy at a constant price, while fossil fuels tend to have volatile prices. Valuing that volatility would about double the price of US methane gas, still without counting its carbon or methane emissions. And if we value secure and resilient energy, renewables are worth even more. Most of the world's dangerous instability today has its roots in rivalry over the unevenly distributed fossil fuels that renewables can put forever behind us. And since modular renewables are small, cheap, and quick to build, they can sustain lots of experimentation and rapid learning, while a single massive thermal project is still under construction. Solar capacity alone is surpassing every other global source of electricity, while battery storage surpasses pumped hydro storage. Notice in the left graph how many rivals solar capacity has exceeded in just a few years. A year ago, renewables and batteries were the cheapest choice to make about 85% of the world's bulk electricity. And they cost less than just operating about 3/4 of existing power plants. Thus, Bloomberg confirmed that the cheapest way to meet a flat load is now solar or wind power plus backup, which can come from efficient and timely use, or storage, or renewables, or generally the costliest fueled generation. So this is why 3/4 of the new firm capacity being added now in India is solar plus batteries. Renewables can also be incredibly fast to build. A year ago, North America's biggest microgrid was built in 4 months in Sparks, Nevada. Redwood Energy laid 20 megawatts of photovoltaic panels on the ground. or where land is costly, the batteries can be safely, cheaply, and compactly stacked up. Then Redwood Energy used novel power electronics and software to combine the world's biggest array of second life automotive batteries, about 800 electric vehicle battery packs, each wrapped in a white tarp and set on cinder blocks, into 62 megawatt hours of unified storage. Those batteries provide 2 to 48 hours of storage as needed for a few years, then they get hot swapped and recycled. The result is a 100% solar, 24/7, 365 power supply, delivering 12 megawatts for on-site modular data centers, more reliably than grid power and cheaper than its 8 US cents per kilowatt hour price. Solar microgrids are safe, silent, virtually water and maintenance free, zero emission, profitable, scalable, and, if necessary, portable. This is what AI speed, ultra reliable, clean power looks like. Gas, coal, and nuclear are not. A recent Australian innovation slashes solar system costs perhaps by as much as half by eliminating frames, single module handling, racking, wiring, and foundations. Folded up, pre-assembled modules unfold from a hinged stack in a shipping container into long pre-wired rows that can easily be attached to land or structures or over water or crops. Of course, many people in Taiwan believe that there is not enough land here for solar power. This would be more convincing if we saw solar panels on any of the buildings, but it's very rare. Yet, a paper in Nature 5 years ago showed that the world could run entirely on rooftop solar power. And this can be built incredibly quickly, as we have seen in Pakistan and in Vietnam. Some of the biggest installations are agrivoltaics, solar over cropland. And because this manages the moisture and temperature of the soil, it can actually sustain or increase crop yields. And it's very good also for grazing animals, which like the choice between sun and shade. So there are only 3 countries in the world that lack enough land to run on solar power without even counting wind power, another big resource for Taiwan. Those are Vatican City, Gibraltar, and possibly Singapore, but not Taiwan. Where renewables need a stronger grid, advanced conductor wires carrying twice as much current could nearly quadruple the US transmission addable by 2035. Today's best conductors are even better, carrying 3 and soon 4 times the normal current. They can decongest grids, grow renewables even faster, and make the grid more resilient with smaller, fewer, cheaper towers and far fewer new transmission corridors. A fifth of the world's new cars are now electric, and when they're parked, their batteries can support the grid and provide emergency power directly to buildings using, of course, Delta Electronics equipment. French drivers can already get a subsidized electric car for free, charge it for free, and even make money by selling back up to 21 kinds of services to the grid when the car is parked. In Europe, this can earn about $1,000 per car per year, several times the driving cost. Another powerful path to a renewably powered and resilient Taiwan. But the biggest untold story is about efficiency, about wringing more work from our energy. Around 1975, US government and industry all said that the total energy input needed to make $1 of GDP could never drop. A year later, I heretically suggested it could drop 72% in 50 years. Well, in the first 49 years, it dropped 65%. But just the innovations already added by 2010 could save another threefold, twice what I originally thought, at a third the real cost. With 16 more years of efficiency innovations, now we can do even better, as I'll illustrate next. Let's start with buildings, which use 3/4 of US and half of world electricity. Here are two graphs that IPCC reported 12 years ago, with bigger savings toward the right and lower costs toward the bottom. Among European new buildings on the left and retrofits on the right, the best projects saved up to at least 90% of their energy without raising the cost of saved energy. Many projects toward the top of both graphs did cost much more by not adopting the best practices shown. That difference is a business opportunity, as also for Taiwan. A few examples of what's possible. My wife Judy and I live in our owner-builder house, 2,200 meters up in the Rocky Mountains near Aspen, where temperatures used to drop to minus 44 Celsius. The central atrium of our house, seen here in a February snowstorm, has so far produced 83 passive solar banana crops with no heating system. That was cheaper to build 43 years ago because leaving out the heating system subtracted more construction cost than super efficiency added. Our house helped inspire several 100,000 passive buildings in Europe with no heating and roughly normal construction cost. A Bangkok analog saved 90% of the air conditioning energy with better comfort and normal construction cost. Nearly everyone on Earth lives in a climate between Bangkok and Old Snowmass, Colorado. But wherever you live, integrative design gives many benefits from each expenditure. So the white arch at the top has 12 different functions, but it has only one cost. In 2010, our integrative design retrofit saved 38%, now 51%, of the Empire State Building's energy with a 3-year payback. The owner's latest ambition is 80%. 3 years later, our cost-effective retrofit saved 70%, making this half-century-old government complex more efficient than what was then the best new U.S. office, which in turn is only 1/3 as efficient as RMI's net positive, no mechanicals passive office, which uses about 1/9 the normal amount of energy in the coldest North American climate zone. This Bavarian building uses 2/5 less energy still. Takanaka retrofitted its Japanese, very typical office to save 72% of its energy without disturbing the occupants. Yet all these technologies existed more than a decade ago. What mainly improved is not so much technology as design, and both keep improving. The Dutch energiesprong method of super outsolation can probably retrofit most buildings to net zero efficiency and install in as little as a day. Inside the house, the best heat pumps can heat 6 to 15 units of hot water per unit of electricity. Cooking efficiency can quadruple. I doubled ours just by using Turkish vacuum-insulated pots and pans. In 6 very hot and humid Indian cities, 1.5 million square meters of integratively designed offices used 80% less energy than the Indian norm, with 10 or 20% lower construction cost, 60% less cooling capacity, but superior comfort and satisfaction. Glare-free lighting is delivered throughout by contract. If workers complain of glare and demand blinds, the architect doesn't get paid. But now there's an important new cooling option, delivering coolth radiatively. In this shaded pavilion, Singaporeans stayed comfortable outdoors without cooling, drying, or significantly moving the hot, humid air. At 32 degrees and 80% relative humidity, their body's far-infrared radiation was absorbed by panels shielded by a thin plastic film and cooled by 23 to 25 degree water. Special radiant roof surfaces can now cool that water passively, even in full sunlight or under monsoon cloud, using no electricity. If this approach can be made cheap and vernacular enough to retrofit into the world's hot climate apartments and slum dwellings, that could potentially eliminate global growth in peak electricity demand. Mechanical cooling is common and important in Taiwan. In the 1990s, Li Englok's world-leading practice in Singapore regularly reduced the measured power intensity of standard big building HVAC systems by 66%, as shown in white. That's for the whole system, supply pans through cooling towers, at the design hour. 5 years ago, Mr. Li could raise that whole system saving to 79%. 9.5 units of cooling per unit of electricity. That's shown in red. Adding underfloor displacement ventilation and passive latent heat exchangers could raise the saving to 84% in green. Even more radically in magenta, radiant coolth delivery plus passive radiant heat rejection could probably cut total cooling power to roughly 1/1000th of standard practice with much lower capital cost. Let's try this in Taiwan. What are we waiting for? Energy-intensive materials form most buildings and other infrastructure, and cement and steel release 15% of global fossil carbon. But these materials are mostly wasted by inefficient structural design. Better design could save roughly half those materials. For example, conventional thick floor slabs are about half the total mass of a typical mid or high-rise building, plus structures to support them. The thin corrugated floor slab here at the lower left costs less, builds faster, and saves 3/4 of the cement and all of the steel. Or thin vaulted floors are now sold in Switzerland. The 4-quadrant version at the upper right is simply craned onto its corner supports with no adhesives or fasteners and can later be as easily removed for reuse elsewhere. In its first use, it saves 2/3 of the concrete and emissions at 90% of the steel. Whenever you reuse it, you save 100% of both. Now combine the thin floor slabs with passive design, which eliminates a vertical meter or so of mechanicals at each story. This allows 3 stories with normal 2.8 meter ceiling height to fit in the vertical space now occupied by 2 stories. Cost, complexity, and time fall dramatically. You get about 55% more net rentable space in the same height and the same footprint. And it's cheaper. Why would you build any other way? Industry uses half the world's energy and electricity. My RMI team's latest $60-odd billion worth of industrial redesigns typically found about 30 to 60% energy savings on retrofit, paying back in a few years and far outperforming the brown zone in the upper left, where most energy service companies deliver disintegrated design. The shaded big blue circle summarizes mechanical retrofits in 8 chip fabs, averaging about 40% saving with a 1.5-year payback. Our new build industrial projects generally found about 40 to 90+% savings with lower than normal capital costs. The shaded blue circle is a new chip fab. Our integrative design combines conventional technology with beginner's mind. For example, half the world's electricity runs motors. Half their torque runs pumps and fans, feeding into pipes and ducts. If the pipes and ducts are made not thin, long, and crooked, but fat, short, and straight, their friction drops by 80 to 90+%, 97% in our house. Typical payback times are less than a year in retrofit, instant in new build. Yet this is rarely taught or done because it's not a technology, it's a design method. And few people think of design as a path to speed and scale. But if everyone did this, it could save 1/5 of the world's electricity. To do this magic, we simply make 2 changes in the design process. First, we specify big pipes and small pumps, not small pipes and big pumps. Friction in a pipe falls as nearly the 5th power of diameter. So how fat should the pipe be to optimize the friction? The textbooks say to make the pipe just as fat as will repay its extra cost over the years from the saved pumping energy. But that's wrong, because it leaves out the capital cost of the pumping equipment. The pump, motor, inverters, electricals must all be big enough to overcome the friction. So their size and roughly their capital costs will fall as nearly the 5th power of pipe diameter. Yet the capital cost of the fatter pipe rises as only about the 2nd power of diameter. So when we optimize the pipe as a component, we pessimize the system. Instead, optimizing the entire system yields fat pipes, tiny pumps, so the total capital cost goes down. The second design change is even simpler, therefore harder. We lay out the pipes first, then the equipment, not the reverse. So traditionally, we put the tanks, boilers, and so on in convenient, arbitrary places. Then we ask the pipe fitter to come connect point A to point B. But by then, A and B are far apart. Other stuff got in between. They're at the wrong height. They face the wrong direction. And by the time the pipe snakes its way across the space, all dressed in neat right angles like they teach us in trade school, the friction is 3 to 6 times what it should have been with a straight shot. So we should design out friction by using fat, short, straight pipes, not thin, long, crooked pipes. Efficient piping layout may look odd. Engineers who are used to seeing big, powerful pumps may think someone made a mistake with the decimal point when they see the tiny pump on the right, but the measured performance leaves no doubt. Notice also we raise up the pump to meet the pipe rather than bending the pipe down to a pump on the floor and back up again with 4 elbows. I'm currently writing an illustrated how-to manual called The Tao of Pipes, 光道之道, 划分为准. It's a hilarious dialogue between 2 fictitious Chinese factory engineers discovering together how to untangle their pipe noodles. Applying these concepts at the Oakland Museum in California, Peter Rumsey retrofitted an efficient layout into the condenser water pumping loop. This cut the energy for pumping by 3/4 with a 2 or 3 month payback, and it eliminated 15 pumps that will never again waste energy and maintenance costs. When he also repiped the chilled water loop and added variable frequency drives, this doubled the flow and saved 85% of the energy. To help the pipe fitters understand how to minimize friction, he simply asked them to lay out the supply pipes as if they were drains. Because in another part of their brain, they know that drain pipes, whose flow is driven only by gravity, not pumps, will clog if they're too small or have too many elbows and joints. Here's how most big buildings pipe cooling tower water back to the condenser. But if we lay it out instead the way Peter does, everything gets better. less space, weight, noise, friction, energy, fewer parts, smaller pumps and motors, less installation labor, less maintenance, higher uptime. The only obstacle is force of habit. We should bend minds, not pipes. In a Dutch industrial case, this approach cut pumping energy by at least 7-fold. Actually, the engineer measured it at 12-fold, with lower capital cost. And as a free bonus, it also saved 70 kilowatts of heat loss with a 2-month payback because it was easier to insulate short, straight pipes. But belatedly, I realized we had left out 8 additional benefits we could have captured, each justifying even bigger savings. I later estimated that if we'd properly valued these extra benefits, we would have saved not 86 to 92% of the pumping energy, but probably around 98% with even lower capital cost. Now think of the whole power and pumping system. From the fuel burnt at the thermal power plant to the end use, many successive losses compound, so only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left, they become compounding savings, and every unit of flow or friction you save in the pipe saves 10 units of fuel, cost, emissions, and global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. Combine that now with 35 improvements to the motor systems as you make those 5 or 10 times smaller, and you raise the potential electric savings from 1/5 to 1/3 of the world's electricity. That's not in any official forecast, studies, standard textbooks, or climate models. Again, because it's a design method. Now think about this in a classical data center. 2/3 of the fuel fed to the thermal power plant is lost in the plant and grid. Half that electricity is lost in the cooling system and uninterruptible power supplies before reaching the servers. Half the server energy does not reach the chips because it's lost in inefficient, usually very underloaded power supplies, not made by Delta, and in lots of fans to take heat that largely shouldn't be there off the motherboard into the room so we can do dumb things with it. The next problem is severe underutilization of computing resources, partly through lack of virtualization. So the resulting energy flow is so small it's about to vanish, so let's magnify it. Next comes bloatware, running many unnecessary threads and processes and making simple tasks very complex because the compute cycles were cheaper than programmers' attention and someone else bought the energy. Downstream of all that, you may even have inefficient business processes. So altogether, a few hundred thousandths of the original input energy in the fuel ends up delivering customer value. Where should we start fixing this? Downstream. First, we write elegantly terse code, efficiently compiled, with the goal that every compute cycle is needed and wanted. I had assumed this might save an order of magnitude in compute cycles. Actually, it's 2 orders of magnitude, and with today's AI slop, it might be 3. And now this is important because we use mobile devices, and efficient code stretches battery life. Well, then we can at least quadruple server efficiency more nowadays. The servers need much less cooling and power supply, and there are much smarter ways to do that, and we can even cut utility losses in half by using fuel cell trigeneration for lower total capital cost. So you multiply these savings from downstream to upstream, and now it seems you get 2, maybe 3 orders of magnitude savings. In the project for which we made this diagram, our partner EDS said that if our recommendations had all been adopted, we would have saved about 95% of the total energy and half the capital cost. In fact, the client rejected most of those suggestions that EDS agreed with, so we could only triple the efficiency at the same cost. Very disappointing. But progress continues and adoption expands. In just 8 years, the world's data centers had enormous growth shown on the left in all their parameters, but almost completely offset that activity growth with a combination of efficiencies, the blue bars. So computing went up 550%, electricity use went up only 6.5%. In the past few years, AI-boosted growth might be changing this pattern, but that may not last because electricity used per unit of AI services is falling by about 4-fold per year. In 2003, we convened over 90 industry experts and together found ways to save about 89% of data centers' energy use. And these findings proved influential. So instead of a data center commonly using 2.5 units of energy per unit used by the servers, the world record is now 1.02. But the collective potential of further efficiencies, especially in software and system architecture, can cut electric intensity by 5 orders of magnitude or 10 orders of magnitude with optical chips, just demonstrated in China. Maybe we can even approach the computing efficiency of the human brain. Now, Paul Westbrook and I co-led the redesign of this Texas Instruments wafer fab to use 40% less energy with 30% or $230 million lower construction cost. So it was built in Texas, not in China or Taiwan. Its system efficiencies eliminated one of the 2 utility floors. It inspired cutting company-wide chip-making energy intensity by 70%, water 62%, greenhouse gases 72%, with further gains to come. We helped another major chip maker discover how to save roughly 2/3 of a new wafer fab's energy use and half its capital cost. We could replace all 22,000 tons of chillers with any of 3 cheaper to build natural cooling methods, over 10 times more efficient than electric chillers, but far cheaper. The group set 3 levels of increasingly ruthless ambition: no brainer, no regrets, and no prisoners. And this graph does not show the savings in all the cooling and other auxiliary equipment when you save a unit of tool energy. But actually, if you count those interactions, the ambitious scenario on the right would be at least a factor 4 below a base case the client thought was close to optimal. And of course, many of our innovations now are inspired by nature. An Australian sea captain, Jay Harmon, in California and Australia, has developed a new kind of hydrodynamics. He noticed this ropey Fibonacci spiral as water ran out the bathtub and thought that must be the minimum energy shape for that surface between air and water. So he asked, if I make a pump rotor that shape, maybe it would be the most efficient rotor. So he did. If your 100,000 kilometers of fractal blood vessels had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But in fact, your 1/3 of a kilogram, 1.5 watt heart is big enough because your blood follows nature's standard design, laminar vortex flow. And now that we know how this works, pumps and fans using such Fibonacci shapes can raise efficiency by about 20 or 30%. In fact, the hydro turbine on the right even lets fish pass through unharmed. And the latest rotors in little fans, the latest at the bottom uses 70 to 85% less power per unit of flow than its competitors from Holmes and Vornado and even Dyson, while providing higher airspeed with much less noise. Motors, too, keep getting smarter, more efficient, now often 97 to 99%, and in the past 5 months, shockingly lightweight. The British 1,000 horsepower motor on the right produces an astonishing 59 peak kilowatts per kilogram. And that enables revolutionary vehicles. But 2/3 of the energy needed to move a car is caused by its weight. BMW showed how integrative design can lightweight a car at competitive cost, even at 2013 carbon fiber prices. I drive such a car. It made money for all 250,000 units, and its carbon fiber was paid for by the batteries that its lightness saved. And fewer batteries mean faster recharging with less electricity, infrastructure, emissions, and investment. This car's integrative design snowballs weight savings much more than usually assumed. Its manufacturing is radically frugal. It eliminates the 2 hardest, costliest steps in automaking. It's much better for workers, and its efficiency is quadrupled without compromise, 53 kilometers per liter equivalent, with many driver advantages. Lighter, lower drag big vehicles are also emerging. This Tesla semi-electric truck entering mass production this year has 3 to 6 times normal efficiency. This quiet diesel air taxi can fly from Taipei to San Francisco using 1/8 the fuel of a typical business jet, and can scale up probably to 777 size. Now we can even use lattice and membrane structures to save about 98% of the weight in metal aeronautic structures. What's next for electric cars? Solar-powered ones. 2 light and sleek ones ready to enter the market as soon as they finish raising production capital get 107 with 5 seats or 146 kilometers per liter equivalent, that's 2 seats, 2 or 3 times more efficient than a Tesla, so efficient that they run just on solar power from the roof of the car for ordinary driving of about 20,000 kilometers a year without plugging in. And if we apply the same thinking to airplanes, I think our grandsons may fly all solar-powered airlines across the Pacific. If you want to know how to apply the 10 pillars or principles of integrative design that can produce such results, the 15 lectures from our Stanford course are posted free at efficiencyhub.stanford.edu, and soon we will post the slides with their presenter notes. So given these efficiency examples and hundreds of others, let me caution you against the assumption that electrification will need several times more electricity. Over 33 years, Norway used only 24% more electricity as its car fleet became 1/3 electric. 63% of its fairly efficient housing stock adopted heat pumps, and its GDP grew by 105%. Norway was well electrified to start with, but this example still casts doubt on very high electricity forecasts. So we have, as also in Taiwan, a huge efficiency potential, which makes renewables faster, cheaper, and easier to install. And we need vision and will to put all these moving parts together. But I think the basic conclusion is that we should go forth and be fruitful and subtract. Thank you.